All right, let me get the chat box up here. And let's see. Perfect. All right, before we go ahead and get started, how was everybody's weekend? Anybody do anything fun? Nope. Nobody? Nothing? Took the MCAT. Well, that's exciting, Alex. Do they give you those results right away? 2 weeks. Bummer. Work double shift. Man, well, I guess that's at least good. You're being able to pay the bills here. So I assume everyone watched my Washington football team beat up on the Eagles on Sunday. Because if you didn't, I'm probably going to fail you for the class. But yes, it was. Dwayne Haskins, indeed. Really, I could just talk about the Washington team all class, but that probably wouldn't be good. I have not uploaded these slides yet. Let me actually think to do that right now. All right, so while I am doing that, what did we learn last time?
How to standardize scores.
How to standardize scores. And why would we want to standardize scores, Kenya?
So they can be translatable onto different scales. For example, translating from the IQ score scale or whatever to another scale so that it.
Yeah, exactly. Fantastic. And yeah, Nancy, you're right. We did that with z-scores. Perfect. And so who remembers the equation for a z-score? I don't know why this is being so temperamental here.
Standard deviation. Can you hear me?
X minus mean over the standard deviation. Exactly. Fantastic. And somebody else, what is X? Oh, is somebody talking?
X is the exact data score.
Yeah, exactly. So X is whatever point you're interested in. Good. All right. Let's see. All right. So that should now be up and ready to go. Questions about what we covered last time? None? All right. Fantastic. Well, we are moving right along. Today, we are going to be talking all about probability. Let me move that over. And just for ease of bouncing back and forth, I'm just going to leave it like this rather than in presenter mode. But you should all now have access to these slides themselves. So, fun fact of the day. If you have a feeling you've experienced an event before in real life, it's called deja vu. I am recording, yes. Thanks for asking, Apollonia. If you feel like you've previously experienced an event in a dream instead, it's not called deja vu, it's called deja rive. I don't know how you would actually pronounce that, but there you go. There was a faculty member where I did my PhD whose research was all about deja vu. Because I'm sure we've all had that experience wherein you're like, not only do I feel like I've been here before, I feel like I can project what's about to happen. And everybody thinks they're special and that unique, myself included. But in reality, it's just kind of this false sense of knowing or understanding. But it is it's a weird phenomena, very weird phenomena indeed. All right. So today, like I said, we are talking about probability. So I've kind of mentioned this up to this point of we want to know whether something's due by chance or if it's likely representative of some state in the world, right? And so when I talk about flipping a coin, right, the question is it more likely to come up 100% heads when you only flip it twice? Or is it more likely to come up 100% heads when you flip the coin 50 times? Well, obviously, it's more likely to come up 100% heads when you flip it twice, right? There's a 25% chance that you're going to get both heads, right? That number gets infinitesimally small when you look at getting 50 heads in a row. And so we're saying, what is the probability that just by chance, if I flipped a coin 50 times, I would get 50 straight heads? Well, we all know that, I mean, we can all intuit that that probability is very small, right? And we may even colloquially say things like, oh, that can't happen. In reality, it can happen, right? Because we're dealing with probabilities. There's always a non-zero probability when things are not, in violation of the laws of physics or things like that. But we're talking about, okay, how likely is this? And based off of that likeliness or that likelihood, we're then going to make a determination about the world. So, like I said, yeah, it's essentially determining a ratio by comparing the frequency of occurrences for an outcome relative to the total number of possible outcomes. Right? And so let's think again, just flipping the coin twice. Well, it could come up heads, heads. It could come up tails, tails. It could come up heads, tails, or it could come up tails, heads, right? So each of those outcomes has a 25% chance, right? There is a 1 in 4 probability that you will get heads, heads when you flip the coin. And so when we think about the relationship between populations and samples, so somebody remind me, what is population again?
Isn't it the total number of participants in any experiment?
So it's not just the experiment, but it's the entire, yeah, exactly like Kenny said, the entire group of interest. And so let's say I wanted to see if there was a height difference between UAH and UAB students. The entire population of UAH and the entire population of UAB would be my population. The sample would be the 30 people I picked from UAH and the 30 people I picked from UAB, right? And so there's a certain probability that goes into selecting a specific sample, right? And so if I pick 30 people from UAH and I see that their average height is 6 feet tall, if I know that population distribution, from there I can infer what is the likelihood that I would have selected people who are 6 feet tall just by chance, right? From that probability, or from that sampling, we can then do a series of inferential statistics, right? And so inferential statistics, as we're going to be covering for the rest of the semester, are those things that tell me, okay, is this due to chance or is it likely indicative of a state of the world? And so the inferential statistics are going to allow me to say, okay, better than a certain degree of probability, I am pretty well assured that the average height of 6 feet tall is in fact representative of UAH students, And then it'll make more sense as we go along in the semester, but that just serves to highlight it. And so again, within probability, whenever scores in a population are variable, which is to say they move around, it's impossible to predict with perfect accuracy exactly which score or scores will be obtained when you take a sample from the population. So again, if we know the distribution of all the heights of people at UAH, we know there's variation in there. And it's impossible to predict exactly what each score will be, but we're relying on probability to determine the relative likelihood for specific samples. So what would be the this is a rhetorical question. What would be the probability of picking a sample with an average height of 5'3"? Or what would be the probability of selecting a sample with an average height of 5'8", etc.? And so again, in each of these cases, we're relying on that probability to understand how likely it is. Because if something's very unlikely, has a really small probability, we're then going to say that the fact that it happened is most likely due to the fact that that coin is in fact weighted, right? If we get 50 heads in a row, we know that's such a small probability of that actually happening that we say, okay, it's probably the case that that coin is weighted so it always comes up heads. Even though it's possible that it would always come up heads just by chance, it's very unlikely. So because I can't see y'all, if y'all have questions that come up throughout this, feel free to just go ahead and type them into that chat box or unmute yourself, etc. It's a little hard for me to gauge exactly how well y'all are able to pick up on this without actually getting to see you. And so to reiterate, probability is important because it establishes that link.
Excuse me.
Yeah, Sonny, what's up?
In the last slide, I wanted to ask, what do you mean by variable?
Does it move around, right? So is there a distribution of scores? Does that make sense?
Yeah, thank you.
Good question. So again, probability is important because it establishes that link between samples and populations. For any known population, so any population, excuse me, you know the actual distribution. So we'll talk today about like IQ and SAT scores, etc. But for any population where you know what those scores are, it's possible to determine the probability of obtaining any specific sample. And so there's a lot of text on the slide, but I wanted y'all to be able to have kind of access to all that information after the fact. So the general goal of inferential statistics is to use the information from a sample to reach a general conclusion or an inference about an unknown population. So all this is saying here is that when we're using inferential statistics, we are going to try and essentially make an educated guess about a population from a sample, right? And so when we adhere to good research principles like random selection, random assignment, things like that, that in tandem with kind of our probabilistic estimates are going to allow us to have some foundational understanding of what that population actually is. And so if the sample has a high probability of being obtained from a specific population, then we, as the researchers, can conclude that the sample is likely to have come from that population. So if we find the average height of UAH students based off of our sample is 5'6", that probably has a high probability of being the case, right? Or it seems very likely that we could get a sample with an average height of 5'6" from the population. Kenya says the shared screen is stuck on 6 minutes ago. Slide 5. Is that the case for the rest of y'all?
Not for me.
No? Huh. Yeah, I don't know what to tell you, Kenya. I'm sorry. If you want to, yeah, try restarting it. It's all recorded, and so if you need to come back, you can jump in. But sorry about that, Kenya. Thank you all for the help there. So if the sample has a very low probability of being obtained from that specific population, then it's reasonable for the researcher to conclude that that specific population is probably not the source for the sample. Right? And so if I sampled UAH students and got an average height of 7'1", it's very unlikely, very low probability that that is representative of the UAH population. And instead, maybe I accidentally sampled a whole bunch of basketball and volleyball players on their way out of practice. Right? And so now we can say probabilistically, it's likely not the case that that sample I have represents that whole population. All right, so I'm going to pause real quick. Does anybody have any questions about this so far?
So the main thing about inferential statistics, they just pretty much help us draw conclusions about the total population.
Exactly. Yeah. So think back to the Mythbusters example I talked about first day of class. The Mythbusters tend to just look at the averages and said, yes, there's a difference, right? But you're always going to get a difference just by chance, right? If I sampled 100 people from one group and 100 people from another group, even if they're the exact same, just either sampling error or small variations day to day or things like that are always going to give us at least some small difference. And so inferential statistics are saying, okay, what is the likelihood that that difference is due to chance? Or is it due to the fact that these two samples, are representative of different populations? Good question. What other questions do we have? All right, well, if you have any of them, feel free to go ahead and type them into that chat box, and we'll go ahead and continue here. And so remember, when we talked about the z-scores, a z-score of 1 is how many standard deviations above the mean. Exactly. Yeah. A z-score of 1 just means 1 standard deviation above the mean. And remember, when we first talked about our normal distributions, we said that about 68% of the population falls between -1 and +1 standard deviations. So about 68% of the population falls between a z-score of +1 and -1. And then I said about 95% of the population falls between -2 standard deviations and +2 standard deviations. And the actual number is 1.96, gives you the 95% in the middle. So a z-score of negative 1.96 and a z-score of positive 1.96 encompass the ends of 95% of the populations. Which means that the 5% remaining are in these two tails here. So 2.5% in that tail, 2.5% in that tail. So this means if you have a z-score of 1.96, you are higher than 97.5% of the population because you're including all of this 95% in here, and you're including the extra 2.5% down here. And so the probability, when we're talking about probability from here on out for the rest of the semester, we're going to be talking about it in relationship to essentially this type of curve. So if you get a score that falls above 1.96, or perhaps below negative 1.96, you can say that there's less than a 5% chance, excuse me, less than a 5% probability that you got that just by chance, right? Because only 5% of the values are in these tails. It's such a low probability that we're going to say it most likely wasn't due to chance and is most likely indicative of this person that you sampled being from an actual different population. So if we think about that normal distribution there, several things happen once we draw a vertical line straight through that distribution. That location can be specified by a z-score, right? And so we draw a line right down here. That can be specified by a z-score of positive 1.96. And that line divides this distribution into a body and a tail. And I will show you an example of that in just a second. So if we're just looking at this here, if we drew this line only at 1.96, just ignore this line over here. If we drew it only at 1.96, everything to the narrow end, we would call the tail. Everything below that would be the body. And so when we're dealing with probability, the nice thing is you don't have to actually calculate that probability. We will reference what's known as a unit normal table, and I'll show you that in just a second. It's actually in the back of your book too. I don't remember what appendix it is, I think A or B. But it's giving you the probability based off of a certain z-score, and it'll give you several different probabilities, and I'll show you that in just a second. But column A for any of these unit normal tables is going to list the z-score values. So the z-score that you calculate, just like we did last time, it will give you that z-score. So when you go to look up your z-score, you're going to look it up in that A column. For every z-score location, so let's say we went and looked up that z-score, the second and third columns, columns B and C, are going to list the proportions in the body and, in the tail respectively. And it's actually labeled on top. So this is not something you're necessarily going to have to memorize. I just want you to be familiar with it when I show it to you in just a second. And then column D is going to list the proportion between the mean and that z-score location. So I'll show you this in a graph in just a second. And so those table values you can now use to determine the probability of something happening just by chance. So let's take a look at a unit normal table. So again, you can see column A over here Just ignore these squiggly lines. This is just to represent that this does not continue and that there would be a whole bunch of numbers in between here. Column A gives you your z-scores, right? So z-score of 0 is the mean, z-score of 0.34, and this continues all the way up. And I'll show you a full, or at least more complete, z-table shortly. Column B gives you the proportion in the body. So let's say you had this z-score was 0.34, right? So this z-score is 0.34. You're 0.34 standard deviations above the mean. This is saying from that z-score all the way to the left is that proportion in the body. So 63.31% or 0.6331 as a proportion of that entire normal distribution falls in the body of the distribution. Column C is a proportion in the tail. And so again, let's say we went and drew this line at 0.34 right here. We know that to the left of that z-score is 0.6331 of the distribution. To the right is the remainder, right? So it's got to add up to 1, which gives you 0.3669, or about 36.7% of the distribution falls in that tail. And then the third column, or excuse me, the fourth column, gives you the proportion between the mean and your z-score. So you can see, if we go back down to 0.34, drew our line there, what is the proportion of the distribution that falls between that z-score and the mean? 0.1331. Right? And this should make sense because we know the proportion from the mean all the way over, you should have 50% on either side of the mean. And if you've got 0.1331 from here to the mean, if you were to add the extra 0.5 to it that you know is on this side, you would get the same value as if you just took that z-score and took everything in that body. And when you add it, so add 0.1331 to 0.5, you get that 0.6331, just like you would expect.
Wait, I'm sorry. Why
Yeah.
did you add it to 0.5?
Because if you were, it's just a sanity check, right? And so for your proportion between the mean and the z, you've got this value here, the 0.1331. And just to give you kind of comprehension of what's going on here, everything on either side of the mean, so to the left of the mean is 50% of the distribution, to the right of the mean is 50% of the distribution. And so the distance from the mean to z is the extra little bit that you get from that body, right? So to the left here, you have 50% of the distribution. You have this little distance in here that represents the 0.1331. And so all I'm saying here is with this same z-score as you had up here, you've got that 0.1331. If you just add that bottom 50%, that'll give you the same value for column B. Does that make sense?
Yeah,
Great.
thank you.
Yep. All right. So let me quickly, I'm going to pull up the iPad here. Stop that share. All right. So when we talked about that body and tail, we had our distribution here. we had our z-score here. So this is our z-score. Everything to the left of that z-score was the body. Everything to the right of that z-score was the tail. Now, if you have a negative z-score, that flips, right? So this is for a positive z-score. If you're doing this for a negative z-score, you'll have that same distribution. And now let's say we have our z-score here. Our tail now becomes this part, and our body becomes this part. So anytime you are looking for the tail, you're looking for essentially the smallest of these two spreads, right? So this would be the tail, this would be the body. Going back here, this is bigger, so this is going to be the body, and this will be the tail. Questions about that? Because that's going to be important when you start looking things up. This may be silly, but what about when you have a 0 z-score? Yeah, no, that's a great question. That's not silly at all. Then it doesn't really matter because, let me just show you real quick. If you've got a 0 z-score, you know that 50% falls to the left and 50% falls to the right. So you could just pick, right? If you have a z-score of exactly 0, it doesn't matter which one's the body and which one's the tail. Does that make sense?
Yeah, it makes sense. I'm just wondering, like, I guess what kind of question would that be? You would answer. I don't know.
So if I said, you know, the mean IQ is 100, what's the probability of me getting a score that is 100? You would have.
So it's 50-50.
Yeah, not quite 50-50, but yes. Yeah, I mean, so once you go back to the actual z-scores here, you can see there is a 0.5% chance that I would get a z-score of, or excuse me, yeah, I would get a z-score of 0, or I would get the mean value for that.
Okay, cool.
Good question. Good question. All right. All righty, so let's go on here. Nope, I don't want to move that. All right, so to find the probability corresponding to a particular score, or that X value, you first have to transform that score into a z-score, just like we did before. So once you get that z-score, you're then going to go look that up in that, excuse me, unit normal table. So to show you just another example, here's somebody from University of Dayton who has just put together a z-score table for us. And so let's say I know the mean is of IQ is 100. I know the standard deviation is 15. And so somebody gets an IQ score of 130, right? So that's 2 standard deviations, or a z-score of 2. And so I want to say, what is the probability that somebody would get a 130 or higher? So I'm looking in the tail. So now I go to my z-score of 2. I look above. So this is column C, right? So this would be in the tail. And I see 0.0228, right? So probability of 0.0228, or essentially 2% chance that somebody will have an IQ of 130. If, on the other hand, you want to be finding the score or that x value corresponding to a particular proportion, you first look up that proportion in the table. You're going to read across to find the corresponding z-score, and then transform the z-score into an x value like we did last time. So if I go back to this table here, and let's say I wanted to know essentially what would the score be that would correspond to a top 5% IQ score. I would go to the table here and I would look for that percentage in the tail. So this column right here. And I would go all the way. I'd look down, look down, look down, look down until I got to 0.05, right? Because that's 5%, or that 0.05 probability. And I can see that essentially between 1.64 and 1.65 is that actual value. And so let's just take the smaller one. This would be my z-score, right? So I now have my z-score of 1.65 that I can plug into with the known population mean and the known population standard deviation to find what IQ score corresponds to the top 5% of the population. And we're going to do some examples here of that in just a second. So you're going to be relying on what we covered last time to find the z-score from an x, from a known x, or to find an x from a known z-score. So we're going to do these together. We want to find the probability associated with z-scores of these kinds. And this is how we write it, right? Big P parentheses. So the probability of a z-score greater than 1. So if we're looking up a z-score, or excuse me, the probability of a z-score greater than 1, are we going to want the proportion in the tail, in the body, or between the mean and the z-score? Tail, exactly. Yes, good job, Ace. So exactly, we want to know what is the probability of a z-score greater than 1, right? So z-score, we get to 1, and we want to know what's the probability greater than 1, right? So now we're in the tail. If we said what's the probability of a z-score less than 1, it would be the body, right? Because we go to 1, and then what's smaller than 1? Everything over here. So in this case, we go to a z-score of 1. Everything in the tail is what we're interested in. So probability of a z-score greater than 1. So let's go and let's find 1 on our z-score table. And there is 1. And we're interested in the tail, or essentially above the z-score. And that gives us 0.1587. Let's see, did we get that right? 1587. Perfect. All right, so what's the probability of a z-score less than 1.5? Do we want the body or the tail? Body, exactly. Good job, Skylar. Yeah, so let's go back to our unit normal table. Let's look up a z-score of 1.5. We're scrolling over here on the left-hand column, and we keep going. Perfect. So we find our z-score of 1.5. We want to know what is in the body or below that z-score. 0.9332. Let's go look this up. 0.93. Perfect. Exactly. All right. So now let's say we've got a probability. We want to know the probability of a z-score less than negative 0.5. Do we look up the body or the tail? Tail, exactly, Nancy. Perfect. Yeah, so remember when we went back to our earlier example, whatever is the smaller side, right? And so in this case, that z-score, you know, if we've got our entire, let's go ahead and share. So again, if we're looking up that negative z-score in here, what's over on this side is that tail. And I know it seems like I'm overemphasizing this, and it may seem pretty self-evident and obvious, but people get tripped up on this every time. And so I really want you to make sure you understand that which one you're going to be looking up on depends on if you're positive or negative. So a z-score of less than negative 0.5, so we go to a z-score of 0.5, because they don't go into the negatives there, so 0.5, and we're going to want the tail. And so we find that tail value of 0.3085. Did we get that right? 0.31 when you round, perfect. All right, so now in this last problem, we want to find the probability of a z-score between negative 0.4 and positive 1.25. So let me go ahead and share this once again. So if we draw this distribution, we want to know what is the probability you'll have a z-score of negative 0.4 and positive 1.25. And we want to know what is the probability of a z-score in there. And there are a couple ways to do that, but the easiest is to rely on the proportion from the z-score to the mean, right? And so we know that that fourth column gives us this value for each side. And so we'll just add them up. So if I go and look up the probability, excuse me, if I look up the probability of a z-score of 0.4 between the mean and z, that gives us a probability of 0.1554. Now I want to get the probability of this side over here. And so I go and look up the 1.25. And between 1.25 and the mean is probability equals, or proportion equals 0.3943. Yes, exactly, Evan. So when I add those up, so 3943, 1554 gives me 7, 9, 14, carry the 1, 5497. And let me go ahead and stop this. Share the screen again. And when I look down here, I round my 5497, gives me 0.55. So now we can get the probability that we have each one of those values. What questions do we have at this point?
Okay.
Oh.
Can we just do one more example like the last one we did?
Yeah, sure.
Okay,
We
so-
will actually
alright.
go over a couple of those in just a second.
Oh, okay.
Sorry, somebody else was speaking too.
Sorry, but she might have asked mine. What did she ask?
Can we do another couple examples?
Oh, yeah. That's pretty much what I was going to say.
Okay. Ace, where do we have access to the z-score table? So that'll be in the back of your book. Yep, thanks, Kenyon. You can also just type in unit normal table, and you'll get a variety of ones that come up. So this is what came up when I typed in unit normal table on Google. It was one of the first options. So you also have access to relevant components for your exam when we get there. All right. So that just goes over what we just did of how we get the actual values to add them up. Now, let's go ahead and do another couple examples. What is the probability associated with z-scores between negative 0.67 and positive 0.67? So let's go ahead and share once again. All right, so we've got our distribution here, and we want to know negative 0.67 and positive 0.67. And we want to know what is the proportion found in between here. And so we will go back to our unit normal table, 0.67, and we're in column D here. We want to know what is the probability between the mean and the z. So we get from our negative z to the mean of 0.2486. And then we also know, because it's just positive, that that probability will also be 0.2486 over on the right-hand side. And so 2486 times 2 gives us 2, 1, 16, 17. Carry the 1, 489 gives us 4. So 0.4972 should be that answer. And when we look that up, crap. And when we look that up, we get 0.49. And actually, I rounded incorrectly there. Should probably be 0.50. But so just about half of the distribution falls between negative 0.67 and positive 0.67. So now let's go ahead and do for a z-score between 1 and 2. This one may seem a little trickier. I will walk you through it here. So we've got our distribution again, and we want to know what is the probability, or what is the proportion of that distribution between a z-score of positive 1.0 and positive 2.0. So there are a couple ways we could do this. You could think about taking the proportion in the tail from 1 on and subtracting this little bit. Or you could think about, okay, what is the distance from the mean to z here, and then subtracting that mean to z here, right? So there are a couple ways to actually go ahead and do it. I like doing it this way that I just illustrated. It just works better for my brain. I don't know why. So let's go ahead and find what is this blue value? What is the distance from the z-score to the mean here? And when I look up a z-score of 2.0 in my unit normal table, from mean to z gives me 0.4772. And now I'm going to want to subtract this red value, right? Because now what I really care about is just this distance, right? And so I already have the blue. I need to subtract the red to give me just this area in there. And so when I look up the z-score for 1.0 between the mean and z gives me 0.3413. Whoops, that's a 7, not a 3. And so to get this yellow value in here, I'm going to take that 4.4772 minus that 0.3413. Subtract that, 6, 9, 5, 3, 1, 1359 should be that answer. So let me go ahead and share that screen again. Gives me, whoops, I rounded incorrectly again. So let's make this crap. Let's see, 1.4, or actually let's do 1359 for that. Does that make sense how we got there?
Yes.
Perfect. Questions about that?
So basically, if it were, would these be, so when we have these on our test, are we going to be given a table, or are we going to have to find the z-score for like a certain given number, or?
No, you're going to have to memorize that entire table.
Yeah, that's okay.
No, I'm kidding. You don't have to memorize it. That would be awful. That would be so mean. No, you will be given part of the table that's relevant.
Okay, to the question, correct?
Yeah, so I would give you something like, all of these values in here and say, what is the proportion in the tail for a z-score of 0.96? And so you'd have to know how to read what you had gotten here.
Yeah, okay. Thank you.
Yep. Yeah, I don't know who I was talking to, but man, you were a champ for taking that in stride of being willing to memorize this entire table. No, you don't have to memorize that. Other questions so far? Cool. So here's just another practice example. We've already gone over how to get that, but we're running a little short on time, so just practice that on your own at home. And if you can get that, you've got a good understanding of how to actually get these probabilities. So now let's move on to some more concrete examples. So let's say the SAT test has a mean of 500 and a standard deviation of 100. What's the probability of selecting a person with a score of 650 or more? So what is the first thing that you guys think we need to do?
Find the z-scores.
Exactly, yes. Find the z-score corresponding to that 650. So, share once again. All right, so we know the equation to get our z-score is x minus the mean over the standard deviation. And so we know our mean is 500 and our standard deviation is 100. And so for our x value of 650, we're going to do 650 minus the mean of 500 over the standard deviation of 100, which is going to give us 150 over 100, which just gives us 1.5 for that z-score, right? And so now, if we go look up that probability, of a z-score of 1.5, we're going to want column B in the tail. And so the probability of selecting somebody with a score of 650 or higher is 0.0668. So about 6.5% chance that we're going to select somebody with an SAT score of 650 or higher. So if we go look at that, yes, 0.067, perfect. We are rocking and rolling. What's the probability of selecting an individual with an SAT score between 600 and 700? Well, this is going to be like that last problem we worked with the probability between 1 and 0. We go ahead and get this rocking. So again, we've got our distribution. We know our mean is 500. And we want to know what's the probability of somebody having between a 600 and a 700 SAT score. So we have to find the z-score for the 600 and for the 700. So we know that if our mean is 500, we know our standard deviation is 100. We know that the 600 is a z-score of 1. We know that 700 is a z-score of 2. Right? And so this just goes back to that exact example we ran before, right? So what is the probability of getting between a z-score of 1 and a z-score of 2? You're again just finding the distance from the mean, or excuse me, from the z to the mean. So in this case, that blue line here. You're then going to subtract the distance from the z to the mean for this, for the 1. You get that all together, you should get 0.1359. And so when I go back to our PowerPoint and we look this up, boom, 0.1359. So now we have, whoopsies. Now we have the question of what score is needed to be in the top 15%. Show the desktop, there we go. All right, so what we have to do is go find the probability that corresponds to 15%, or 0.15. And we're interested in the top 15, so 15% in the tail, right? And so let's scroll. We're looking at column B, and it looks like between 1.03, 1.04. Let's see what we actually selected for this. So 1.04 is what we'll go ahead and use for that z-score. And so now we just put that z-score into the equation that we went over last time for how to calculate the x given a known z. So get this up. So if we know our z and we want to get our x, we take our x plus, or equals the mean, plus the z-score times the standard deviation. So if we know our mean is 500, so that equals 500 plus z times 100, or 500 plus 1.04 times 100 equals 500 plus 104, which is equal to 604. And so now we go back to this. What is the score needed to be in the top 15%? 604. So if you got a 604 on your SAT, we know that you are in the top 15% of students who take the SAT. Questions about that so far?
I wanted to ask about the percent. Like, how did you find the number on the chart?
For which value? For the 15%?
15%. Yeah.
Yeah, so the 15% is just that probability. So if I go back to our unit normal table, I know I want a 15% or higher in that tail, which means I look in this column B and find 15%, or actually find the proportion that corresponds to 15% in column B. And you can see.
Why did you choose the tail?
Because I'm interested in what is the score that corresponds to the top 15%, right? And so if I look at the actual distribution again, pull this up. I want to know, based off of this distribution, what is the score that corresponds to the top 15% up here, right? I don't care in this case about the bottom 85%. Does that make sense?
Yeah.
Okay, great.
Thank you.
Of course. What other questions do we have? Would it be the same number for bottom 15%? No. Well, depends on what you mean by the same number. It would be the same z-score, but the actual SAT score would not be, right? So just think about this conceptually. If you want to look at the top 50, okay, perfect. Perfect. Now, your z-score would be negative 1.04 for the bottom, but it would still be 1.04. All right, let's go ahead and push on. If you have any other questions, go ahead and type them into the chat box. So when we talk about percentile rank for a specific X value, we mean the percentage of individuals with that score or below. And so if somebody came to you and said, I have a score of 137, an IQ of 137, what is their percentile? How many people have an IQ lower than they do? And so that would be the exact same thing that we just did, except now you're going to be finding the z-score associated with 137, and you're going to find everybody in that in the body of that distribution. And so we know that they are 2.5 standard deviations above the mean. And so if we go to our z-score and we find 2.5, scrolling down, we're looking in the body, they are in the 99th percentile for IQ. Hopefully that makes sense. We're running a little bit out of time, so I want to go ahead and push on, but I'm happy to stay after class if y'all have questions. So we can then use probability for binomial distributions. And binomial, just like the name would suggest, by two means they are formed by a series of observations which have exactly two possible outcomes. So heads or tails, true or false, right or wrong, etc. We can identify those two outcomes as A and B. So the probabilities of A being represented by P and the probabilities of B being represented by Q. I skip a slide here? All right. So when the number represented by Pn of A outcomes and the number of B outcomes represented by Qn there are both greater than 10, the binomial distribution is closely approximated by a normal distribution, such that the mean is equal to P, or the probability of A. So let's say probability of a heads on flipping a coin by the number of trials. And so let's say you flip the coin 50 times. The probability of getting a heads on any individual trial is 0.5. N would be 50, so that number of times you flip the coin. So 0.5 times 50 would be 25. And 25 would then be that mean that you're looking with, or that you're working with, rather. To find the standard deviation, you take the square root of N times P times Q. So we'll go over an example in just a second, but just know again, P is the probability of A, Q is the probability of B, N is the number of trials, number of coin flips. So when the binomial distribution is normal, a z-score can be computed for each value of x. And then we just use that unit normal table like before. And so this comes into play with a question like this. So suppose you were taking a multiple choice test with 4 options per question. If there are 48 questions, what's the probability that you get 14 or more correct just by guessing? Right? So we know our probability of getting any one question right just by guessing is 1 in 4, right? You've got 4 options per question, A, B, C, and D. If you guess, there's a 1 in 4 chance that you get it right. And there is a 3 in 4 chance that you get it wrong. And so that Pn, which is how many should you get just by chance, is the probability, so 1 in 4, times the number of questions, 48. And so chance would dictate that you should get 12 of those 48 questions right just by chance. Similarly, it also then dictates that you would get 36 of those questions wrong. So let's actually work this out. So P is 1/4, Q is 3/4. We know our Pn again is 12, our Qn, so the probability, so the number we should get right just by guessing is 12. The number we should get wrong just by guessing is 36. And so again, because our mean is that Pn, we know that the mean we're going to be using for the z-score in just a minute is going to be 12. The standard deviation, again, is just the square root of N times P times Q, or 48 questions times the probability of getting any individual question right, 1 in 4, times the probability of getting any one of those questions wrong, 3 in 4. That comes out to 3, right? So 48 times 1/4 gives you 12, times 3/4 gives you 9, square root of 9 gives you 3. So now we have our mean and our standard deviation for this. And we just calculate our z-score like we have before, right? So our z-score is x, our x value, minus the mean, divided by the standard deviation. Or in this case, we could rewrite it, which says the exact same thing, of our z-score is equal to x minus pn. So the number you should get if choice was the only dictate, divided by the square root of n times p times q, or p times q times n. Right? Doesn't matter which order you put them in. And so I want to know, what is the probability that I get 14 or more correct by guessing? Well, because we're using real limits here, we're going to choose 13.5 instead of 14. Minus that mean, so 12, that we got just by that quarter probability, 1 in 4 chance, for 48 questions, which should just give us 12. So 13.5 minus 12 divided by our standard deviation of 3, which gives us 1.5 divided by 3, or 0.5. And so we know that with this z-score, what we have to do is go to our unit normal table again, go all the way to 0.5. And the question was asking, what is the probability that you would get 14 or more correct by guessing? So we know we want the tail, right? And so if we go to our z-score of 0.5, we find in column C the proportion in the tail. This says 0.3085. Go back and look at this. Yep, 0.3085. So this is saying there is a 30.8% chance, 30.9% chance that if you just guessed, if you closed your eyes and just guessed on every single question, you would get 14 or more, or I guess technically 13 and a half or more. So now we could do that example with coin flipping. So let me open this up. So let's say we flip the coin 40 times, and in that 40, it came up heads 27 times. Came up tails, that remaining 13 times. And so now we can work this all out. So what is the probability of it coming up 27 times, right? And so we know our p-value, our p is 1/2. So the probability of heads, probability of heads is equal to 1/2. The probability of tails is equal to 1/2. So this is Pn. So 1/2 times 40 gives us 20. Qn, or 1/2 times 40, gives us 20. Right? And so now when we go back to our equation, our mean is going to be that P in. Our mean is going to be 20. Our standard deviation is going to be the square root of n times P times Q, or square root of 40 times 1/2 times 1/2. So 40 times 1/2 is 20, times 1/2 is 10. The square root of 10 is give me a second. Hey Siri, what's the square root of 10?
The square root of 10 is approximately 3.16228.
There you go. Siri solving it for us. Let's say 3.16. All right. So we have our mean, we have our standard deviation, and we know our x is 27. So to find our z-score, we take 27 minus our mean of 20 divided by our standard deviation of 3.16, which is equal to 7 over 3.16. And now 7 divided by 3.16 gives us a z-score of 2.22. So if we go look up that z-score on our unit normal table, our z-score of 2.22, there we go, in the tails. So there is a 1.3% chance that if you flip a coin 40 times, it will come up 27 times or more as heads. Does that make sense? What questions do we have?
In that example you just did, where did the 1/2 come from?
It's just the chance of getting a heads, right? So there are two options.
Yeah, okay.
Yeah.
Yeah, I get it.
So on a dice, the chance of rolling a 3 would be 1 in 6, right? Coin flip 1 in 2, multiple choice 1 in 4, etc. What other questions do we have?
Okay, so when we're looking at the table, the with the z-score, the probability just gives us the percentage of what is either above or below. And all we have to do is use that number or that percentage to figure out everything, right?
Yep, exactly.
Okay.
Skylar said, when we're calculating the z-score, should we always use the lower limit of our x value? Truth be told, let's say yes. I was going to say truth be told, it doesn't really come into play all that often. But for the exams, go ahead and use the lower real limit. I'll likely not take off points if you don't use the lower real limit, just because I'm not always specifying what the ranges are. But for something like a binomial thing where you can't get 13.5 questions right, at least just on a multiple choice, we would assume that that real limit would be 13.5. So go ahead and do that. But if you can't make assumptions, or you can make an argument that it's impossible to know what that real limit is, feel free to just use that actual number itself. I mean, because I just did. So what was the answer to the probability of the coin flip example, Ace? The answer was, if we go back to our unit normal table, we had the z-score of 2.22. So the answer was a probability of 0.0132, or a 1.3% chance. Of course. All right. I will hang out here and answer any questions that come up. let's go ahead and plan on class being in person for those of y'all who come on Wednesday. I got the rapid test. The rapid test came back negative, and the brain swab type test should come back in the next day. And so if you hear back from me saying we're going online again, we'll go online, but let's operate under the assumption that we will be in person on Wednesday for those of y'all who come in person. So I will go ahead and hang out here. If you have any questions, I'm happy to answer them. Otherwise, I will see you all on Wednesday.